Okay, BC, here's some filling in the gaps and showing you some examples of working out this Taylor series stuff. So it says find a power series for that thing, for f of x equals tangent inverse of x. So now we know there's two different ways to create a power series. One is that we could use a geometric series. And the nice thing about that is that if you've got geometric series, you already know what to do with the interval of convergence. You already know when it's going to work because you know what the that the ratio has to be between -1 and 1. So it's like, oh, okay, that makes it kind of easy. Like that part of it is going to be a kind of a piece of cake. The second part of it, the second way to find a power series for something is to use the Taylor series stuff. But then we're kind of stuck a little bit because we don't know how to find the interval of convergence. Like we don't have like an easy way to do it like we do with the geometric series because we don't have that built-in ratio thing. So, but let's show you a couple more examples of the kind of thing that you can do in terms of working out what a series is and finding its interval of convergence. So this one, f of x equals tangent inverse of x. You might look at that and say, okay, that does not look geometric. But actually, you can do this with a geometric series, and that's the easiest way to do it. The reason why is that these functions, you can work with the derivatives or the antiderivatives of these things and then work backwards to figure out the one that you want. Let me show you. I can go tangent inverse. Well, tangent inverse of x, I can think the derivative of this is 1 over 1 plus x squared. I mean, that's the derivative of tangent inverse. That's geometric. You might say, well, what are you talking about? Well, I can write it as 1 over 1 minus negative x squared. And now it's geometric. So piece of cake. So this thing, 1 over 1 plus x squared, is just equal to, first term is 1 minus, it's minus because the ratio is negative x squared, so minus x squared plus x to the fourth minus x to the sixth, and so on. Okay. Take the antiderivative of both sides, and so you've got tangent inverse of x is legitimately equal to, and we don't mean approximately equal to. This is the difference between the earlier stuff with Taylor, is that the earlier stuff with Taylor, we said we were just going to make a function that would be pretty close to the, we're like a polynomial that's pretty close to the function we're talking about. And you've got a built-in error, and we kind of just accepted that. Now we're saying, okay, what if we do this to infinity? So we keep doing more and more and more and more terms. Then, in theory, there isn't an error as long as this thing converges. As long as the sum that I'm creating converges to that function, then there is no error, and they're just equal. So tangent inverse of x then is just the antiderivative, which is, got to pop up, there we go, which is antiderivative x minus 1/3 x cubed. Notice there's no factorial in this one. Plus 1/5 x to the fifth minus 1/7 x to the seventh, and so on. And that is a power series. That's a power series on the right-hand side for tangent inverse of x. And the only thing is that we'd like it to match at x equals 0, because that's the center of this. That's the center of this expansion. But you can see tangent inverse of 0 is just 0. And so all these terms are going to be 0, so it works. I don't need a constant to make it line up. And so, boom, I've got the Taylor series. I've got the power series, and I didn't actually use Taylor to do this one. So that's what you're doing I'm just seeing if there's any others in this section I want to do. I'll sneak preview because I think we need one more example. Later on, we had this one. This happened I put this in the 9.10 notes. And 9.10, the idea is that you're going to use your old building blocks to create new ones. And so we're going to do that with this one here. So let me get that again. That's g of x is 2x over 1 plus x squared. So g of x equals 2x over 1 plus x squared. And it says find a power series for this one. So we just want a polynomial series that's going to be equivalent to this thing. Okay, well, what I'm going to do is I'm going to separate this. I'm going to write it as 2x times 1 over 1 plus x squared. Okay? So that's equal to 2x times, and I've got an infinite series now that I can put in for 1 plus x squared. I could have generated it by myself, but it's on the same page, so what the heck, I'll use that. And that's 2x times x minus 1/3 x cubed plus 1/5 x to the 5th, and so on. Sorry. And now I can multiply the 2x into this infinite polynomial, and I end up with 2x squared minus 2/3 x to the 4th plus 2/5 x to the 6th, and so on, minus 2/7 x to the 8th, and so on. And that's in power series for that function. Now, one thing to notice is that this isn't going to work all the time. Like, for example, like suppose they said make a power series for e to the x over 1 minus x. And make a power series for this. You couldn't do this trick on this one. You can't say, oh, it starts at e to the x, and then the ratio is x. So x e to the x plus x squared e to the x, and so on. Find a power series, if that was the instruction for this thing. You're like, well, why not? Why can't I do that? Well, the problem is this isn't a power series technically, because power series just has x squared, x cubed, and so on. But this has e to the x in there, right? That's not going to work. But what I could do that would be legal is I could say, well, I could separate this, so not a power series. Sad face. But I could say, well, hold on a second. I know that I could separate this into e to the x times 1 over 1 minus x. And I've got a representation for e to the x. That's what we did at the very end of class. That's just 1 plus x plus 1/2 x squared plus 1/6 x to the cubed plus ... plus 1 over n factorial x to the n, okay, times this one, because I can represent that as a power series. 1 plus x squared plus ... And in theory, you could FOIL this. Now, I know it's infinitely long, so you're not really going to FOIL it. Some of the questions that sometimes get asked on something like this is they say, what in the power series for this function, give the quadratic term, the x squared term. And so you could look at it and go, oh, okay, the x squared term, well, I could multiply 1 times x squared. Okay, I got x squared. I could multiply x times x, that's 2x. So that's another x squared, so that's 2x squared. And I could multiply this one times this one, and that's 1/2 an x squared. So I've got altogether 2.5. I got 5/2 x squared. So you could like FOIL part of it, but you'll never be asked to FOIL all of it because that would be ridiculous. Okay? So what do we have here? This is like showing another example of the geometric series stuff. And what we have out of this is that we can make geometric series for other functions by using their derivative or using their antiderivative in order to do that. So for example, that's kind of what we were doing with natural log. The tricky thing with natural log is we couldn't center it at 0, because if we centered it at 0, natural log of 0 isn't defined. So that's why we had to center that one at 1, and it was critical that we do that. But, whoa, sorry. There you go. But But that was the first part. And the second part is, if we don't have a geometric series for something, then we can make a Taylor series for it instead. And that can create a power series. There's the e to the x over 1. I did 1 plus x there. Yeah, I'm just deciding which one I want to do here next. Just deciding. Okay. Yeah, no, I think I'm going to stop it here. And I'm just going to kind of reorganize this stuff so it's a little more cohesive. Of how do we use the two parts? One, how do we use Taylor? 3 parts. How do we use Taylor series for these things? The second one is how do I deal with the interval of convergence if it's a Taylor series? How do I know when it converges? Because if it's geometric, I can figure out when that converges. But if it's Taylor, then I'm like, when does that converge? I don't really know. So we have to do that. And the third one is, how can I use these building blocks? Can I use these to create any other functions? So that's what we're going to see in the next video.